Hello, everyone. Oops. Hi, everyone. 5-minute warning. We have 2 incredible talks tonight, so we are going to have to keep on schedule. So grab another drink, grab another slice of pizza, grab a seat, and get ready for some great talks in 5 minutes. Hello, everybody. As you can see, I'm not Matt McClure. For the second time ever, Matt is not making the meetup and has asked me once again to step in. And once again, I tapped some of the smartest people I knew. Yushi bailed me out a year ago and is coming back again to make a fantastic meetup. The goal of tonight is to make sure that Matt knows that we didn't miss him at all, that we all had tons of fun without him and had some great talks without him. But we hope he's back next time. So, first of all, if you haven't heard of it by now, you should have heard of DMUXed, the conference for video engineers, happening October 17th and 18th. What's that? I had all this set up. You know what I'm saying? This is what this is what happens when an amateur steps in. What can I say? If you haven't heard of it by now, DMUX, the conference for video engineers that grew out of the SF Video Tech meetup, is happening October 17th and 18th. We have an incredible speaker lineup this year with some very cool speakers. Oh, hey. It's going to be happening downtown San Francisco. And if you haven't grabbed a ticket yet, please do so, because we are somehow, even though we've increased the size of the conference by 100 people again this year, we're looking at perhaps running out of tickets. So if you want to come, and we would love it if you come, just head on over to dmuxt.com and grab a ticket. It's going to be at Bespoke, which is like hopefully a lot fancier than the place we were in last year. Not that the place last year didn't have charm. It was just maybe a little cramped charm for all of us. Yeah, big shout out once again to all the great sponsors for DMUXed. And also a great big shout out to Heavybit for hosting this meetup again. And without further ado, I'd like to introduce our first speaker for the night, Yushi Shen from Twitch.
All right, thank you. Can everybody hear me? Hear me all right? Okay, perfect. So thanks, Nick. It's just been a fantastic year. I talked on this stage about this time last year. So that's been a year. So how are you going, everyone? So today I'm going to talk about the VP9 live transcoding system that Twitch is going to push into production by the end of this year. And when I was preparing these slides, I was thinking, wow, it's actually a pretty complicated story to tell. But I hope that by the end of this presentation, I bring you two pieces of information. The first one is for this talk, I'm really not talking about how the codec is designed. I know you guys all are experts. You know the 64 by 64 or the 35 modes of intra-prediction and AS, all these filtering, all these mathematics. I'm not going to talk about that. I'm more talking about from the user's point of view. What is the logic chain to convert these fantastic features into business values, into the better user experience that we can offer to our viewers? So that's the first piece of information. And I'm thinking about my second piece of information. I'll come back to that. I'm sorry. Okay, say a few words about myself. For people who don't know me, I think I know most of you. For people who don't know me, I'm working for Twitch. I'm in charge of core video technology at Twitch. I'm in charge of the transcoding team, but also working on the player. I actually invented AV1 switch frame, which I will cover a little bit at the end of this talk. For my early career, I coming from a linear TV industry, so I work for chip company. I build equipment for TV stations. So I do come from a codec background, but now I'm doing streaming right now. So from a codec builder to a customer. Okay, so now say a few words about Twitch. I want to do a little survey. Any of you do not know what Twitch is? Wow. Or you are shy. And any of you have seriously used the Twitch? Like, okay, not too. Okay, thank you very much. Let me actually show a little intro video to you, and I just double click. How can I get audio? Oh, sorry, the audio doesn't work somehow. But just So while the gentlemen are fixing that, let me actually explain where. So we are the world's biggest live streaming platform. Try again. Okay. Not really. Again. Okay.
No,
that's
perfect.
not
a thing.
That one.
Okay. The high tech is so difficult to get right, but nevertheless, here we go.
By classics, but he might fall and continue to get ball control. Look at this play from Cronovia. Big aggressive move by South Korea.
What? No, that's not a thing.
These beautiful individuals.
Oh, so does watching my stream. That's so cool.
You're teaching it the meaning of life.
Here's the hard carry. This guy is unstoppable.
It's a very simple thing that you can do even if you've never seen it before.
Let's get more butter.
Say hi.
Oh, good goal. That's it, baby. What a way to end. Wow, what a game.
Okay, anyway, so you know that for people who haven't used Twitch, you have missed so much fun in your life, right? So, so I already showed that. So, really, that from an engineer point of view, I think the two biggest value that Twitch offer to this industry are two things. First, is we greatly reduce the barrier of doing broadcast. You don't really need to have an uncle who's a director in Hollywood. You just need to have this simple setup, and you have internet. You can broadcast on Twitch. And the only teeny tiny thing that you need to worry about, you need to find people who want to watch your video. And the second one is because of the low latency. So I was actually chatting with Netflix. Gentlemen, we were talking, so for our latency, for the low latency feature that we released at the beginning of this year, for our end-to-end latency, from the moment the video hit our system, which is ingest point, to the video that's played out by our player, the median is 3.5 seconds. So in this scenario, you can see this guy is playing the game, and people are chatting with him, and he needs to respond to these chat message in a timely manner. So this guy is actually a great gamer, but he's also a great entertainer. So he needs to, like, multitasking, playing the game and also chatting with his people. So in this way, the audience are actually part of the content, and that makes Twitch so interesting to watch. So that's Twitch in a few words. And because we are mainly doing the esports and the gaming content, so we actually build a social network. It's a community of gamers. People come to Twitch to watch other people playing game and also to socialize with other gamers. This is Twitch's scale last year, and we've been consistently growing. So that's the number last year. This year at TwitchCon, which will happen in October, our CEO will announce this year's number. So I expect it will be much bigger. Okay, so just one example is a few months ago, actually in June, 2 months ago, E3 is the biggest gaming conference. And during this conference, we hit our new concurrent viewer record, which is 2.9 million. Next is the Alexa. I think many of you are familiar with this index measuring the popularity of website. So if you look at our history from 2011 when Twitch was launched, we've been growing, like climbing up this ladder pretty consistently. And according to Alexa, we are the third most popular video website behind YouTube and Netflix. And I guess the second speaker will talk about what's going on there. So these are the background, but so I was mentioning in the beginning, I still haven't remembered what the second piece of information I want to tell, but I'll come to that. So because of this scale, because of the content we are servicing, why do we need to, what is the motivation for engineer to put together this next generation transcoding solution? And really it's coming from a business need. If you look at the 1080p60, this is the feature that we released in 2017, beginning of 2017. This actually reminds me of a story. I was working for OnLive, which is a cloud gaming company, and that didn't go very well, so it went down. So I was looking for a job, so I come to Twitch. And when I was interviewed, and at the end of that interview, my manager, who actually, he was the last interviewer. So he just basically come in and say hello to me, making sure everything went well. So he was asking me, he said, Yoshi, what do you feel about Twitch? So I say, so I just, without any thinking, I just say, your video quality really sucked. And for that moment, I really regret. I think this is such an impolite answer to such a nice question. And he wasn't angry. He said, yeah, well, that's great. Sounds like you are motivated. So after I received the offer, I actually call him, just say thank you and check a few things. And I was asking him one thing. I say, what do you want me to do at Twitch? He said, I don't know what you want me, I don't know what I want you to do. The reason I hire you is you come to our team and you yourself figure out what you want to do. And I would say, well, that's a really fantastic answer. This is really the fantastic team that I want to work for. So I actually, so I'm living in South Bay, so I commute 2.5 hours every day to come to the city to work, and that's been fantastic. Anyway, so back to that, the 1080p60 is one of the long-awaited feature that our community needs. And once we release that, it's really fantastic. Believe it or not, majority of our viewers can watch 1080p60. And that's due to 3 reasons. The first reason is our broadcaster really have good internet connection. So uploading 6 megabits per second is not a big deal for them. And in fact, in some Asian countries like Korea, Singapore, they even want to do 9 megabits per second. So they really have this bandwidth. And on the other hand, for the last mile, our viewers, most of the viewers do have very good connection. So they can watch 6 megabits, it's no problem. And in the middle, our Twitch, one of the biggest value of Twitch is we build our own CDN. We make huge investments into building POPs around the world and building this replication network, the backbone capacity, and also the last mile, the edge capacity, pairing with ISPs. So we really have the whole system that's going pretty well. So a good problem to have is, so on the right is the quality ladder that the transcoder just spit out, all the way from 6 megabits 1080p60 all the way down to 160p30. And just using the number, of course, not everyone can watch 6 megabits per second, but assuming majority of people can watch 6 megabits per second. So 6 megabits per second times 3 million is the concurrent viewer, this the peak, which actually give us the peak traffic is 17, 18 terabits. That's actually not a small number. I just give you one reference point. In the news, I read Akamai during the World Cup, they claim their peak traffic is about 22.5 terabits per second, which means Twitch's peak traffic is actually not too far away from the Akamai's World Cup peak traffic. So which means we are really offering good service to our viewers, but on the other hand, delivering 17 terabits traffic, it's not very cheap. Okay, so here, after we talked with our product manager and went back and think about, so this is the product requirement he kind of threw to engineers. So our next-gen codec format and the transcoder need to really satisfy these 2 requirements. So first of all, it must be live. We are not a VOD service. We cannot afford spending 9 days to encoding 1 hour of video. Every 1 second of video must be finished in 1 second. So we have to have live. So this is the must-have. And on top of that, our quality standard is X264 median. And maybe for live, so for VOD, people were saying this is not very high bar, but for live, it is actually pretty high bar. I will give you the detail in a minute. So live and high quality, then our goal is to save at least 25% of the bit rate. So based on these three requirements, the engineer go out and do all these studies, and our conclusion is using FPGA doing VP9 can deliver this requirement. So now I'm going to explain this, this thought process where we do this feasibility study, what kind of information we have collected, what kind of logic we have followed, and why we come up with this decision. And when you're thinking about video compression, like a video standard, of course, intuitively, you were saying, I only need compression gain. I don't need anything else. But on the other hand, it's actually the opposite. The first thing you need to think about is the legal risk. And because of the situation of the legal risk, that determines the status of the ecosystem, of the decoder ecosystem. And based on that, that determines the codec company make investment in which format. And that determines the encoder's performance and determines compression gain. So the logic is from the legal risk to ecosystem of decoder, then the compression gain. So let me explain the legal risk first. For HEVC, as all you know, that there, instead of having one patent pool, the MPEG LA, now it has 3 patent pools. And what makes things even worse is there are some patent holders, they are actually outside of these 3 patent pools. And what this means is, compared with H.264, H.264, the cap is $10 million. So any company want to use H.264, just pay $10 million, you're done. It's great. But for HEVC, because 2 multiple patent pools, the cap is easily $40, $50 million. It's much more expensive first. The second is, even if you are a very good customer, you really want to sincerely pay each patent holder, it's very difficult. First, the 3rd patent pool hasn't published the patent policy, so their royalty policy yet. And also for other patent holders, you really need to negotiate one by one. And that is actually impossible for a company to have an army of lawyers to negotiate with all these patent holders. So just not feasible. If you want to seriously pay the patent fee. On the other hand, VP9 is the opposite. VP9, Google said, so this is the quotation from their legal, what's it, the license scheme. So the first term said it's no charge, it's free forever. And the second one says, if any company decide to sue Google or sue any VP9 user, this company automatically lose the right to use VP9. Okay, which means, so if I'm Samsung, I want to sue Google, then I just have to remove VP9 from my product. And that's also not practical, okay? So based on this situation, from our study, we think VP9, the legal risk is much smaller. And because of that, they're looking at what's being supported in the browser. So the things we care most are Chrome and Firefox, at least based on our data. Majority of the browser traffic is on Chrome and Firefox. So they don't support HEVC, and I talked with their team, they will never ever support HEVC, but they support VP9. And one simple reason is HEVC is just so expensive. It's just Mozilla, just as an independent organization, they just cannot afford. But for, of course, Apple's Safari and Edge, I think, Edge, Microsoft Edge, they support HEVC. The traffic on that is really small, so we kind of care less about. If for any of you, if you want to make decisions, you need to ask yourself, do you care about the traffic on Firefox and Chrome? If you care, VP9 is probably a better choice for you. And on the other hand is the mobile, and that's also interesting. Of course, for H.264, since the dinosaur age, on every device, everyone supports H.264. Okay, that's great. But on iOS, of course, Apple, they only support HEVC. They don't support VP9. They probably will never support VP9. On the other hand, iOS is only 15% of the market share. 85% is on Android. And on Android, according to our study, is so if you look at the Android spec, since 4.4, it actually supports HEVC. VP9. And for VP9, it's all the hardware chips support VP9. And according to our study, according to our test, that they all support hardware decoding. But for HEVC, it's a little bit complicated. I actually asked many people, I asked many companies. I really don't get a very good answer. So one concern is because of this royalty risk, this legal risk, although Android 5.0 said you have to support 480p 60 for other resolution, is depending on the hardware, and the chip do support HEVC. But because of the royalty issue, a lot of OEM manufacturers, they actually turn off HEVC support. So if you really want to deliver HEVC on mobile, for Android, you really have to test every device one by one. And at Twitch, at least at Twitch, we have seen 1,500 devices. So you really need to test all of it. So that's why I put a question mark on it. And again, for the connected TV, smart TV, and for set-top box, seems in this area they support both. Every device support both, apart from Apple TV. So this is the data that NG Kodak put together in last year, about a year ago. So according to their study, they claim the VP9 installed base is 3.3 billion, while HEVC still big, but it's about 50% of that. And the reason is what I just described. So that's the decoder support. It's because of the legal risk, then come to the decoder support. And next come to the compression gain. So this cartoon is, so actually we have talked with a lot of, trust us, we have talked with a lot of companies, commercial encoder product. We want to just spit out this very simple requirement, and it's actually very hard. I actually don't understand why. I mean, I work on Kodak chip before. I work for Umbrella. We build, our chip is used by almost every prestigious encoder. But so this seems to be a very, very high bar. And so I just cannot, sorry, I cannot, due to Amazon policy, I cannot mention any of the product name, the commercial product name, but I just use X264 as an example to explain why X264 median is a high bar. So according to our test, of course, it's based on our gaming content, based on our software, based on our CPU. If you use X264, only if you tune, like you use the very slow preset, you can just get 11.5% of the bitrate savings. And if you look at encoding speed, it's just encoded at a quarter of the original speed. So even at X264 median for our transcoding ladder on the big CPU, it's pretty big CPU, we can just run median. So running X264 very slow is not practical. It's just too slow. It cannot keep up, cannot deliver the real time. So that's X264. And this is my study note. So then because H.264 cannot deliver us the compression gain that we want, we just have to look at the next generation, HEVC and VP9. So this is my study notes. I guess many of you are experts, so I'm not going to explain each of them. But according to my study, my theoretical understanding, HEVC and VP9 in theory, they are very similar. They're really similar. They have a lot of common features. It's very similar. Which means from a standard, from theoretical point of view, HEVC, VP9, so not too much difference, although they're both much better than H.264. Okay, so the difference, the compression gain is really about encoder implementation. It's not about the standard. The standard, where the standard matters is the decoder support. Once the decoder support is there, it's really the encoder implementation. So we look at encoder implementation. So first of all, our test environment is the Twitch's AVR ladder, which I showed in the previous slides, 1080p60 to 160p30, based on our gaming content, based on the transcoder that we wrote, which we believe in last year's DMUX, we claim it's 70% more efficient than FFmpeg. Running on this almost $3,000 CPU, and we can just run medium. And for X265, we found we can just run ultra fast. And of course, ultra fast, the quality is pretty okay. It's actually close to, it's very similar to medium. which means X265 running at real time, it's not designed for real time. Maybe for VOD, it's fantastic. But for our application, it's not that great. And the even worse news is libvpx. That's the only software encoder. Actually, at the time when we do the study, this is the only encoder in the world can encode a VP9. And based on our setup, we can only run speed 6. So speed 6 is the fastest speed, basically means lowest quality. So speed 1 is the best, speed 6 is the worst. We found it's actually way worse than X264. So this again, I just want to state again that we think it's not to do with the standards, it's to do with implementation. So, which means we really, based on all these beautiful data, we just don't have a good VP9 encoder solution. And we find one, which is FPGA. And I have a video that I'm going to show it to you. So I have a video that on the left and on the right, one side is H.264 median, X264 median at 6 megabits per second. The other side is FPGA VP9 at 4.5 megabits per second. And I'm not going to tell you which one is which one. Please use your own eyes to see whether you can see any difference. And let me just play. I think I can stop here. All right, okay, so anyway, so can you tell the difference? Left one is better, okay. How much? Why definition? Okay. So actually you're... Okay, right. So in this case, actually you're right. Actually the left side is 6 megabits per second H.264. So you are right. So H.264 in this case is still better than VP9 4.5. Okay, so that's the result so far. So that's the story I want to tell about VP9. And sorry? Yeah, I think this is okay. First, I'm not a video coder expert in this scenario, but I think yeah, VP9 has because of the bigger macro block, that's kind of like a wash out at some spot. Yeah. Okay. Anyway, so what I want to say is okay. So if you're interested in the gaming content, this is Twitch contributes the gaming content to the AOM committee, and if you're interested to test any of them, they're uncompressed the video content. If you just go to this website, you can download. Just search Twitch, you can see all these. Okay, so I talk about the VP9. This is something we want to put into production by the end of this year. And next, I'm going to say a few words about AV1. We really excited about AV1. And of course, it's not ready right now. The whole ecosystem not ready, but we believe that it will be the video format for OTT streaming beyond the 2020. When the whole ecosystem is ready. And of course, I think many of you have noticed this Moscow State University comparison. It basically says AV1 is great, but look at the encoding speed. It's 3,000 times slower than H.264. So different people have different opinions about that. So some say it's focused on the quality that is great. Some people focus on the speed, say this is not practical. We understand this, but on the other hand, as I said, this is really the reference code. It doesn't really tell it doesn't really represent the quality or speed of an industrial or commercial product. But what we excited about is most of the, actually majority of the high-tech company are part of the alliance. And we hope that in 2020, beyond 2020, this again become a single format that's supported across all the platform. Then we just go back to the very nice age of the only single format. We don't need to support both H.264, HVC, AV1, or VP9, so just go back to one single. That will be fantastic news for our operation cost for our accountant. So again, I want to say a few words about the switch frame. I think Tarek covered that in last year's Demux. I just say a few words about that. This is some idea that I came up with in 2015. And so the idea is when Twitch moved from RTMP to HLS, so RTMP is a push-based streaming format. It's very low latency, but doesn't do ABR switching. So low latency, but not scalable, quality not great. We switch to HLS, which is we can do seamless switching. We have ABR algorithm, but the latency all of a sudden become 10 seconds or even longer. So so the 3.5 second that I mentioned in the beginning of this presentation, it is still HLS, but we do the chunk transferring. But there was one issue, I think, in the HLS streaming is the switching can only happen at IDR frame or keyframe. And because they're very expensive, so you really cannot put too many IDR. You cannot put the IDR frame too frequently. That's going to affect your coding efficiency. And the S frame, the idea is let's just allow some P frame also be switchable. So the idea is just turn off the motion vector prediction and do some K-back just reset at certain P frames. So without sacrificing too much video compression, we can actually switch. So, so my team, Tarek and a few collaborators from Lab 126, we actually do the work, and that was accepted by the AV1. And it's so apart from besides the keyframe, intraframe, interframe, we have a switch frame in the AV1. And I hope beyond 2020 we can utilize this feature to do low latency, large scale live broadcast. That's the story I want to tell. And so a summary is we are a live streaming platform considered as a international TV stations on internet and our scale. In order to reduce the operational cost, we're building VP9 Live encoding solution to deliver the video quality, 25 bitrate savings. According to our study, FPGA is the only available solution in the market right now. Because we want to do live, we want to do VP9, we want to do 25% bitrate saving. I talk a little bit about AV1, and we hope and we believe that it will be supported on all platforms. And for the switch frame feature, that we will be utilize that to do low latency, scalable broadcast. So that's the end of my talk. Thank you.
Thanks so much for a great talk.
Okay.
We have time for 2 questions.
Yep.
You said the switch frame and the P kind of interface. Like, how can you switch if you don't have any reference, right?
Yeah.
If you don't have any reference, it's intra-coded. If it's not intra-coded, I'm a little bit lost at that point.
Yeah, that's a very good question. So if you think about referencing, you're actually referencing 2 parts. One is the pixel itself, the reference, and the second is the motion vector or the motion information. All right. So okay. So if I don't rely on my reference frames the motion information, I only use the pixels, I can actually switch from up to down or down to up. Right? So that's some technical detail which maybe we can talk offline. Yeah. But the idea is for the S frame, you only not using the motion information as reference. You're only using the pixel. But of course, the encoder need to be very careful how to do that.
Like if you are coming from a high resolution, you want to go low.
Low, yeah.
Are you going to scale down the last reference?
So yeah, if S frame always using the previous frame in the decode order to do the reference, and in making sure that every S frame referencing the same content, it will work. To a degree. To a degree. It won't be pixel perfect, of course, but that's not the point. You can scale it. That's right. Actually, VP9 supports reference picture with different resolutions. It's already supported in the VP9. Oh, SVC. SVC is more complicated. It's more like SISP frame in H.264, but SISP is about every switching combination you need to have a special define. Yeah. Yeah. Right.
Another question?
I was curious, roughly, how many people in your team have you dedicated to FPGA? Because it's quite a particular low-level language, complicated.
Yeah.
So I was curious, roughly, how many people are working on that?
Yeah, that's a fantastic. I mean, I come from. I worked for Umbrella before, and if any of you are familiar with this company, they build chip for Harmonic, Ericsson, all these like a top-tier broadcast. And really, unfortunately, all these Magnum, I think some of you come from Magnum, or you come from Magnum. All these companies, you can prove I'm wrong or not. All these companies, they are actually exiting the broadcast codec chip market because there's no market. The reason is, I think our second speaker, they just grab all the subscribers and they use software to encode. So which really make me in a pretty awkward situation that I want good quality live transcoding solution, and there's no ASIC, and as I said, software is too slow. And luckily, Xilinx CEO, in their company strategy, so they want to go into the data center business, and the video transcoding is one of the applications for so like along this strategy. So we really appreciate that Xilinx putting this effort, and there's a company, I can't mention the name publicly, they provide the software solutions, and we just combine them, and it's a solution for us. Yeah. And to answer your question, it is new, and we want to be the first one to use it.
Big hand again for Yushi.
Oh, thank you.
Thank you so much. Oh, I got it. And now I'd like to welcome our next speaker, Zili from Netflix.
Hello? Can you hear me? Hello, everybody. It's my first time being to this meetup. Although I have been watched this meetup for a long time, it's just the commute. But I feel after today, I should probably come here more often because our first speaker has been commute to here to work every day. So I have no excuse. And I also feel like this is a very nice crowd, and it's like a party, right? Okay, so today I'm going to talk about VMAF. So my slides might not be as polished, so it might lacking some of the background, but I want to get a show of hands like among the audience, how many know about VMAF? Which is good. And how many of you have used the VMAF? Also good, kind of. Okay, so it might lack some of the background on this, but I'm just going to try to explain things. So this talk is going to be focused on the recent updates we have on the VMAF open source package, including speed, 4K, and we're adding a confidence interval to the prediction. And I'm going to start by just give you a brief background on how we got here. Right, so VMAF actually started as a research project at Netflix with the intention that we have a vast video catalog, and we cannot afford to do human inspection at every single piece of them. So there has to be a way to automate them. When we evaluate the solutions in the market, we haven't been find one that could fit our purpose. So we decide to go with our own. And how we're going to approach this is that we're going to start with research collaborations with universities. So the first collaborator we have is with University of Southern California. This actually starts in 2013. That's the time before I joined. So after work of a year, we start to have this VMAF, actually the first version of VMAF running in production at Netflix. And we start to adding more collaborators working on this project that includes in UT Austin and University of Nantes from France. Both universities has expert. So UT Austin is with Professor Al Balvik, and University of Nantes is Patrick Lecalé. They're both like expert in this video quality assessment fields. So moving forward, in 2015, we have our first public showing at ISIP, which is through an industrial paper, very briefly mentioned about the VMAF. In 2016, in June, we have this VMAF published on GitHub, and we also have a first VMAF tech blog. In 2017, we have a major upgrade of the VMAF version to 0.6.1. And in this version, we also add a phone model, which can make a more accurate prediction when the viewing condition is through a mobile device. In the middle of that year, we also got supported from FFmpeg, so VMAP becomes something that's being supported in this FFmpeg as a filter. Earlier this year, we have our dynamic optimizer published. This enabled in production, which is a VMAF-enabled video optimization framework. It's been running for encoding our content in our cloud-based platform. And most recently, we have a new release of this VMAF, including a number of features, which is what I'm going to be talking today. So I'm going to be cover a few topics. What's new in this new release? We have speed optimization and included a 4K model. And also, we're trying to have a confidence interval prediction of what the VMAF prediction gives you. In a sense, we want to know like how much uncertainty is in this prediction, how reliable it is, so that people can make more informed decisions. And I'm also going to slightly dabble into a number of upcoming features, and we plan to roll out in this open source package. So speed up. So we made this optimization for this VMAF OSS executable and the libvmaf library. There's really nothing much to talk about except that we add this multi-threading feature. The credit has to go to this guy. This is one of our open source contributor. So we have enabled the multi-threading in our production, but we haven't got to the time to make it available in the open source package. So this Don Tequila jumped in to help us out. And built on top of that, we also add this subsampling feature. So essentially, you can compute VMAF on every one frame of every a few n frames. And by doing that, you actually could meet your expectation. If you want to do real time, you can do this at expense of some sacrificing of certain accuracy. But according to our test, the loss is not as much. And here it basically shows this diagram. If you're enabling this subsampling feature, you're going to get a speed up. But there's also this diminishing return effects. Probably could be more optimized through making the software better. So for the next part, I'm going to be talking about the 4K model. So here is just an overview of how the VMAF framework works, right? So essentially it has two parts. The first part is basically we're trying to extract some of the features you can see as elementary metrics, which will extract using knowledge we have about the human vision system. And we build those features. They will give predictions that's quality-inducing. And in the second step, what we actually do is we collect the training data from doing subjective tests, right? And through a machine learning-based regression model, we're going to be aligning those feature extraction we had with those subjective scores. And this is typically a lab test that we do in order to collect the subjective score, subjective data. Right? This is our collaborator and university nonce and friends. And you can see here is a typical viewing conditions a subject is under. So after viewing a video, they're supposed to vote using this absolute category rating, ACR scale, to vote the video on the scale of from very bad to excellent quality. And what VMAF basically does is to believe that this is going to be a scale that's linear with the human perception of quality, and we basically going to be mapping them to a score of 0 to 100. And we do simple things. We, for the excellent quality, we roughly map them to the score of 100. And for quality that's bad, it's about, we map it to 20. So on the lower ends, we actually have some space so that we can map even lower quality, which is not being tested in the lab. And the assumption we make here for when we test the 1080p model, which is the version 0.6.1, is that so the viewer is sitting in front of the 1080 on the display, which is 1080p TV, and the video itself is going to be 1080p. And there is a height of this display, and we maintain a viewing distance of 3 times the height of the display. And what this one gives you is a viewing angle of approximately 60 pixels per degree. And you might wonder where this number coming from. So this 60 pixel per degree is the critical viewing condition for a viewer to appreciate the details in the content. What we're drawing here is a contrast sensitivity map of the human vision system. So what essentially this one tells you is, you can think of it as a frequency response of the human eye. So how the human respond to giving a stimuli of a certain frequency. If you're going from a very low frequency to a very high frequency, the response give you is different. What you can tell here is that if you go beyond 60 cycles per degree, the human eye would not be able to appreciate any of the details. So the response is 0. So there's a limit on how much you can perceive in terms of the frequency of the signal. And so if you're doing the math, 60 cycles per degree corresponding to about 120 pixels per degree. And why we're picking this 60 pixels per degree is that it roughly matched to 20% of this response. So a point here. Right? So based on this formula, you can see that if you're viewing a 1080p video, the best viewing distance is 3.2 times the height of the display. But we're just using a rough approximation, which is about 3 times the height. So what we can really say here is the VMAF 1080p model is essentially a 60 pixels per degree model. So now the question is, can we just use a 1080p model to predict a 4K video? Because very naturally, you could tend to just applying this model if you have a 1080 4K video, right? Very simple. You just this VMAP could take an image of a video of any resolution, no problem. But we need to understand what essentially it means, right? So if you're doing the math, like according to this geometry, what it tells you is if you're applying this model to 4K video, it's like you're predicting the quality when the viewing distance is 1.5 the height of the display, right? Because essentially, you're trying to predict what if 60 pixels is packed into 1 degree, and this matches this exact viewing condition. And the good news is this is all good because even if we were doing a testing for the 4K, 1.5, the height is ideal viewing distance in order for the viewer to appreciate the details in the content. So this is a good part. On the other hand, if you're applying this model to a 4K video, there are certain things that hasn't been captured. One is the viewing angle, because now you're at 1.5 times the height, so you have a much wider viewing angle in this sense. So there's a matter of the fovea versus peripheral viewing condition, right? Because we know for the human eye, there is a very sharp imaging is